Predict the polarity of the following molecules. To predict the polarity of the molecules, you have to first draw the Lewis structure of the molecule. And if your Lewis structure is not correct, it's not going to work out. You also have to identify polar bonds in the molecule. Polar bonds are identified by knowing the electronegativity. And the third thing you have to do is you have to identify the shape of the molecule, because the shape is going to give you the 3D orientation of the molecule. All right, so those three things have to be done before you can figure out if a molecule is polar. What is meant by polarity? Polarity means that you have dipole moment. Okay, and dipole moment is given by this symbol, okay, mu. So that's what we are going to do. Let's start with the first one, which is PCl3. For PCl3, I'm going to draw the Lewis structures a little bit fast. Okay, so hopefully you'll all be fine with this. So here we have phosphorus, we have 3 chlorines, and on phosphorus we're supposed to have 5 electrons because phosphorus is in group 5. So I'm going to draw a lone pair of electron here, and chlorine is in group 7, so it should have 7 electrons. Okay, so that's the Lewis structure of PCl3. If your Lewis structure is not correct, shape is not going to be correct. Okay, so now, so regarding the second part, which is the polar bonds now, so do we have any polar bonds in this molecule? Yes, we do, because chlorine is supposed to be slightly more electronegative than phosphorus is. Okay, so that's how you draw the polar bonds. So now the third thing we have to do is the shape of the molecules before we get to dipole moment. Okay, so the shape of the molecule then is given by the axe method. You don't have to use the axe method, but I always like using the axe method. So A is the central atom. I have 3 atoms attached to it, and then I have 1 lone pair of electrons in there. So 3 plus 1 means that I have a tetrahedral electronic geometry, but because there is no 4th atom in here, this is going to be trigonal pyramidal, and that is the shape of the molecule. So if it is a trigonal pyramidal, then this is really what the shape looks like. Okay, so it is kind of like a pyramid, and the lone pair is situated on the top. Okay, so if it is a trigonal pyramidal and I have polarity going on over here between these bonds, it means I am going to have dipole moment for this molecule, and the dipole moment is shown going towards the more electronegative elements. So this is how you show that there is a dipole moment, and it is going towards the chlorine. Okay, so this is how it works. So it encompasses a lot of things. Okay, for such a simple question, you have to do so much work before you can get to the answer. Let's look at the next one, which is SO3. For SO3, sulfur is in group number 6, and so it has 6 electrons. So and then we have oxygen, which also has 6 electrons. Oxygen with 6 electrons, oxygen needs 2 bonds. Okay, so I'm just going to go ahead and do that, because I know for oxygen I do need the 2 bonds, okay, in there. So that's what it is, and then I fill in all my lone pair of electrons for oxygen. For sulfur, I'm supposed to have 6 electrons. All 6 of them are bonded, and before you start panicking that there are too many bonds on sulfur, it's fine, because sulfur can have an expanded shell. Okay, so that's all fine. So now let's look at the Axe formula for this one, and the Axe formula for this compound is going to be AX3. So A is a central atom, and then we have 3 oxygens. So if you have AX3, AX3 means that the shape is going to be trigonal. Yes, you're right, planar. Okay, so that's the shape of the molecule. So that's the shape. Now we'll figure out the polar bonds. Now number 2 and 3 you can do either way you want. Okay, so it doesn't have to be in the same order. The Lewis structure has to be done first. Okay, so first I identify if I have any polar bonds, and yes, I do have polar bonds. So oxygen is more electronegative, so it's going to put electrons towards itself. Now this is a very symmetrical molecule. You have oxygen pulling electrons towards itself from all 3 sides at a bond angle of 120. So which means everything is equally distributed. If everything is equally distributed, think of it as a tug of war. Oxygen is pulling from all 3 sides, while sulfur ain't going anywhere then. Okay, so if sulfur is not moving anywhere, then the dipole moment is going to be 0. Okay, so because there is equal pull on all sides, the molecule is symmetrical. All right, so because of that, the dipole moment is going to be 0. Let's look at the next one, which is H2CO. Carbon is going to be the central atom because it's the least electronegative element. It's also on the left side, okay, of all the elements, barring hydrogen. Hydrogen is different. So carbon here, okay, and then oxygen and 2 hydrogens, okay, that we need. Hydrogen is going to have single bonds, and then oxygen is going to have a double bond. Oxygen will also have electrons left over, okay, to it. So now I can do the polar bonds first, or the shape first, it doesn't really matter. So here we'll do the polar bond first here, and oxygen is definitely more polar than carbon is. Okay, and hydrogen carbon bond is quite non-polar. So if you look at the electronegativity table, you will find that if you subtract the two numbers, they will come out to be 0.5 or less than 0.5. Now you will not have those tables, okay, with you in an exam or anything, so you have to kind of just remember this fact, okay. So now let's go ahead and write out the AX formula for this one so we can determine the shape. So the AX formula is AX3 because I have 3 electron groups, okay, 2 for hydrogen and 1 for oxygen. The double bond is counted as 1 electron group, as you know. So AX3 gives me the shape of trigonal planar. Okay, so if it's a trigonal planar, then I have the shape correct here also, okay, because trigonal planar means that the bond angle should be 120. Okay, so the bond angle is quite okay here, so the shape is all fine. Okay, I don't have to redraw the molecule. So now I have to see whether I'm going to have dipole moment or not. And yes, I should have dipole moment because now in the case of the 120 bond angle, one of the atoms here is pulling a lot more electrons than hydrogens. Okay, so oxygen is pulling a lot more than hydrogen because oxygen is more electronegative, and because it's more electronegative, this is how I will draw my dipole moment arrow. Okay, so that is the dipole moment or polarity of the molecule. All right, let's look at the last one now, and the last one is H2SO4. A little bit of a complicated molecule over here, but that's okay. We need to be able to draw these structures out too. So sulfur is going to be in the middle, and then we have 4 oxygens. So 1, 2, 3, 4. Now one thing I want to remind you is that H2SO4 is an acid, and one of the biggest clue about an acid and hydrogen, because acids are proton donors, is that the hydrogen will be attached to something that is more electronegative, which means that the hydrogen will be attached to oxygen. Okay, so you will not attach the hydrogen to sulfur because sulfur is less electronegative. This is not always true, but this is true 99% of the time. Okay, and so here we have the Lewis structure is not quite complete because 2 oxygens are not happy. So I'm going to go ahead and put the double bonds there for oxygen, and everything is okay now except for the lone pair of electrons on oxygen. Okay, so if you keep things simple, you will not get lost, okay, anywhere, because sulfur has 6 electrons, and now I have 6 electrons on sulfur. All of them are bonded because sulfur is capable of having an expanded shell. Okay, and again, I knew that my hydrogens are going to go to the oxygen because this is an acid. All right, so there are so many things involved here. All right, now in this case where you have H2SO4, there are 2 or 3 things going on. So you'll have multiple AX formulas. Okay, you will have more AX formulas because you have 3 central atoms. Okay, so one here, and then one here for oxygen. These 2 oxygens are the same. Okay, so they're going to behave the same way. So let's work with the first sulfur, okay, that we have here. So in case of sulfur, the AX formula is AX4. And the AX4 is coming from the 4 electron groups that you have around sulfur. And that's going to be a tetrahedral kind of a shape. Okay, so this is for sulfur. For oxygen, it's going to be a little bit different because oxygen has only 2 bonds and it has 2 lone pair of electrons. So then the 2 electron groups that are bonded and the 2 electron groups that are not bonded. Okay, and so AX2E2 is a tetrahedral electronic geometry, but this is going to be bent. Okay, So now I have to figure out whether my molecule is polar or not. Okay, so if I draw the 3D structure of this, it's going to look pretty complicated. Okay, so I'm going to give it a shot and see if you get it. So here is that, and then here is oxygen, which is going to be bent, and then here is another oxygen, which is going to be bent. Okay, so that's what it looks like. I'll just draw the lone pair for the oxygen with hydrogen so you can see why it is bent. The other oxygens are terminal. Okay, so the lone pairs on that don't have any effect on the shape of the molecule or polarity. Okay, so now let's look at if we have any polar bonds. And yes, we do have polar bonds. Okay, between oxygen and hydrogen, that is also a polar bond. Okay, so here we have this. So do we have polarity in the molecule? Yes, we will have polarity. The polarity is not because of the tetrahedral. The polarity is because of the bent shape. Okay, because the tetrahedral is all symmetrical. Okay, because this is symmetrical, there is going to be no polarity because of the tetrahedral. But the two oxygens that we have, these two oxygens are the ones that are going to cause polarity in the molecule. So now if you want to show the dipole moment, this is what you can do. All right, and then show the dipole moment. So that's how this works. So if you want to write in effect at the end if a molecule is going to be polar or not, so then you can say, so for PCl3, yes, they had polarity, so you will say yes. Okay, this is a polar molecule. Is SO3 going to be a polar molecule or not? And because of symmetry, this was going to be no. Okay, it's not going to be a polar molecule. H2CO was going to be a polar molecule, yes. And then the last one, H2SO4, is a definite yes.